Swayam Prabha. Digital India. Educated India.
In this lecture, let us continue our discussion regarding partition function and how different thermodynamic properties can be calculated for a single chemical species using the partition function. In the previous lecture, we started discussing about how the different thermodynamic properties can be expressed in terms of the partition function. We started discussing from internal energy and then we derived a few forms. This was one of the forms that we derived. This is another form in terms of 1 mole of the molecules of the gas, and another form here in terms of unit mass. Subsequently, we showed the expression for specific enthalpy, where since we had already obtained the expression for specific internal energy, that was substituted here, and the product P times V was replaced by RT, R being the specific gas constant. Therefore, we came up with the final expression for enthalpy, specific enthalpy, which is given by RT plus RT square, and then the partial derivative of log cube with respect to temperature at constant volume. So, you could as well write it as capital V. Now, we will initiate discussion about entropy, how we can show that entropy can also be expressed in terms of the partition function is what we are interested in over here. And we are trying to recall the entropy expression we had derived some time back in another lecture, and that was derived for a calorically perfect gas. Here, to keep things simple, we have just referred to that. You can also talk about an equilibrium chemically reacting gas mixture, but that just adds some more associated complications. The basic concept would remain the same, and therefore, we choose to do it for the calorically perfect gas form. And here we are of course expressing it in terms of some reference pressure and reference temperature. So, we have a reference state basically, where the pressure and the temperatures can be represented like this, and then we have let us say a final state where the pressure and temperature would be P and T, represented by this entropy equation. Again at the reference state, the corresponding specific entropy is given by S ref. And in this equation, if you watch carefully, that S, the specific entropy would increase with increase in temperature. That is when this term would contribute a positive value and increasingly positive value if T becomes larger and larger, while if there is a decrease in P, that could also increase the entropy value, because this has a negative sign associated with it. Only a reduction in P can increase the entropy, an increase in P would reduce the entropy. So, these are interesting facts which we should notice from an equation like this. Increase in entropy leads to increase in disorder in the thermodynamic system. That is another very important fact. And in statistical thermodynamics, the increase in disorder of the system would mean an increase in the number of microstates. which obviously means that entropy has a functional dependence on the maximum number of microstates. Now, if you were to consider two thermodynamic systems having two separate values of entropy, and the number of microstates in the two systems are W1 and W2 respectively, and then you think about combining the two thermodynamic systems into one, then you will find that in the combined form the individual entropies would get summed up, while the number of microstates that would exist in the combined thermodynamic system, they would get multiplied. Now, why is it so? It is because the microstates, they essentially represent thermodynamic probability based information, and therefore, in the combined system the individual probabilities would get multiplied. Now, the above relationship between individual thermodynamic systems and a combined thermodynamic system in terms of entropy on one hand and microstates on the other can therefore be conveniently worked out if you have a functional form of this kind. So, you have a log applied on the W on the right hand side of this equation, as you can see, and that is what will generate summation of terms essentially, which gives you the idea of summation of entropy, which it finally leads to, and K 1 is nothing but a proportionality constant here. Now, this functional form was first proposed and conceived by Ludwig Boltzmann, and therefore, the proportionality constant, which we have named as K 1 earlier in the previous slide, was named in his honor, and that is what is the Boltzmann constant, small k. Now, this is a path breaking equation in the sense that it is a crucial connection between classical thermodynamics, where we talk about entropy, and statistical thermodynamics, where we talk about microstates. Now, we want to recall an equation which we left behind a few slides or one lecture practically. We want to have the equation for log W, which we had derived earlier. So, here it is, and we would like to deploy it now. Now, in the Boltzmann limit, we know that when the different energy levels are well populated, there is a lot of degeneracy, that means a large number of states within each energy level. Then the situation that would come up as a consequence is that N j would be much less than G j. That means, the degeneracy levels that we have available are quite sparsely populated. Hence, N j by G j, the ratio is much less than 1, and the G j by N j ratio is again much greater than 1. Another approximate relation is what is necessary here, that when you have an expression for log of 1 plus x, where x is a very small number compared to 1, then we can approximate it to x itself. Therefore, if we plug in all these facts, the natural log of 1 plus G j by N j is approximately natural log of G j by N j. Again, the second simplification is this, which is arising out of this fact. Substituting these above simplified expressions in the log W expression that we left behind in the previous slide, we will get this expression, which is a much simplified one compared to the original expression for log W. And we revert to the Boltzmann distribution now, and we write it as follows: N j star written over here in a form where beta is not written as 1 by k T, but just left as beta. It is going to be an endeavor trying establishing the fact that beta is actually equal to 1 by kT through a direct proof. Now, if we do that, then Gj by Nj star would be represented as Q by N e to the power of beta epsilon j. So, beta is now an unknown. When we substitute the above expression in the log W expression that we have derived, we replace W by W max. Hence, combining the above two equations, we get an expression for log W max. Remember that the moment we write W max, the Nj's have to be represented with a star, and the Gj by Nj star ratio is written in terms of the partition function. Now, we try expanding this term by term, and then you can very easily understand the different steps that we have put over here. For example, summation of Nj star will give you N, the summation of Nj star and epsilon j over all the energy levels will give you capital E, and thereby you end up getting a form for log W max. When we invoke the entropy equation in terms of K and W max, this is what we get. So, we get an expression for S in terms of Q. We further invoke the first law expression that we had talked about in a previous lecture. Tds is equal to dE plus Pdv. I hope you remember the basis of this equation. If we take a partial derivative of the above equation with respect to specific volume, which is again equivalent to volume itself, over here we have it in the volume form, then we see that del S del E will turn out to be 1 by T for constant volume. This is of course a result from classical thermodynamics, because we have invoked this equation from classical thermodynamics. Again, if we take a partial derivative of the S equation, which we just left behind here, then what would we get? If we take a del S del E at constant V, then we end up getting K times beta, and that comes up basically from this term. So, this is a result from statistical thermodynamics. So, we have del S del E at constant volume coming from two worlds, but they should give us the same fact. Therefore, once we equate them, we end up getting an expression for beta, which is 1 by kT, and it is basically a proof that we have done for beta, because we had earlier assumed this expression without any proof. So, in course of finding an expression for entropy in terms of partition function, we also get this additional outcome, a very important outcome, that we found a way to establish that beta is equal to 1 by kT. Now, going back to the entropy equation, we can now write it in this form, where we can substitute the beta without pretending that we do not know its expression. So, once we substitute that, it ends up giving a term like this, E by T, and you can easily show that the entropy finally comes up in this form. This form is derived from the E equation that we had already obtained by dividing it by T. We again revisit the first law equation. Why do we do it? We do it with the intention of finding an expression for pressure now in terms of partition function. We have already found the expression for internal energy, enthalpy and entropy in terms of partition function. We are yet to do it for pressure. So, when you take a partial derivative with respect to volume, keeping temperature constant, then this is how the equation looks like. Since we are considering a single chemical species and additionally we assume that it would behave thermally perfect in a thermally perfect manner, then if you were to take a del E del V at constant T, you will end up getting a 0. Now, remember that for a thermally perfect gas model, the CV that would be involved in the E definition will become a function of T, but nevertheless, when you take a derivative of the E with respect to volume at constant T, that will yield 0. Therefore, pressure can be expressed in this form T times del S del V at constant T. Invoking the above equation for S, we get this form. So, the above equation for S, in the sense the one that we left behind here in the previous slide, that is the one we are referring to. So, that is the one we invoke over here, and we are taking a derivative of that equation essentially, and that equation has been expanded in this form for your convenience, just to establish that which are the terms you should be looking for when you take the derivative. So, taking the derivative gives you an outcome like this, that it comes to K n times del del V of log Q at constant temperature, and therefore, finally, you come up with this form for pressure, pressure being equal to N K T times del V of log Q at constant T. Therefore, now we have also managed to derive an expression for pressure in terms of the partition function. We will go back to the definition of the partition function once again, just to revisit it and go a little deeper into the building blocks. So, what is Q comprised of? It is comprised of expressions of this kind: G j e to the power of minus epsilon j by k t, and these have been summed up over all the energy levels which are available. Now, in the above expression for Q, the different energy mode expressions need to be substituted collectively, in the sense that epsilon j would have contributions from the different energy modes like translation, rotation, vibration, electronic, and so on. Now, if we were to go deeper into the physics and try to find expressions for epsilon translation, here would be an expression from quantum mechanics, where h is Planck's constant, m is mass of a molecule of the gas, n1, n2, n3, which appear as squares in the numerators of the terms that you see within the bracket, are quantum numbers which can take only integral values like 1, 2, 3, as well as 3 more parameters A1, A2, A3, which are basically linear dimensions of the system. And since all 3 linear dimensions are involved, we can intuitively understand that there must be a connection with the volume of the system. If you look at the expression for epsilon rotational, then it comes in the form of this, where the j happens to be rotational quantum number, which can take integral values 0, 1, 2, and so on. I represents the moment of inertia of the molecule. H, as usual, represents Planck's constant. For vibrational energy, n is vibrational quantum number, which will take integral values of 0, 1, and 2, and so on, and nu is the fundamental vibrational frequency of the molecule. For the electronic energy, there is no closed form result which is available, and spectroscopic data have to be plugged in order to evaluate it. Now, if you were to substitute these expressions in the epsilon equation, which represents the total contribution, and you sum up over all energy levels as given in the Q equation, then the total value of Q would be obtained. It is evident. Again, if you are interested in looking at the separate contributions from translational, rotational, vibrational, electronic and so on, it will give you some more interpretation. Instead of looking at the total value of Q, you segregate and you look at it. This is the Q translational, which you remember having seen earlier. This is what we had invoked earlier to prove the point that from the translational form, the dependence of Q on temperature and volume comes up. If you were to look at the rotational value of partition function, then this is how it will look like. It of course shows its explicit dependence on I over here, and then the vibrational partition function has a form like this. Every time you see the dependence on temperature being visible from these expressions, that means depending on what temperature you maintain for the gas molecule, different extents of these partition functions will exist in the system. For the electronic form of the energy, it is expanded in a form of a series here in terms of the degeneracies and the exponential terms containing the energy levels. And for the different electronic energy levels, you need to have spectroscopic data, which has to be directly substituted in the terms involving epsilon, epsilon 1, epsilon 2, etc. And for higher energy levels, epsilon 1 is a very large quantity. You may remember from the energy diagrams, we try to establish that the jumps are extremely large compared to the other energy modes, and therefore, no more than the first three terms of the above series, like the way we have shown over here, only retaining three of them in an infinite series practically, or a very large summation. Only three terms need to be considered, at least till temperatures of the order of 15,000 Kelvin or so, which is a rather high temperature. So, we got some glimpse of how the different modes of energy reflect in terms of the partition function contribution. Now, when single chemical species is considered, thermodynamic properties can be evaluated over a wide range of temperatures, because we already saw that Q, translational, rotational, vibrational, electronic, all the forms that you can think of have explicit dependence on T. Therefore, you can very well understand that since the thermodynamic properties are now expressed in terms of partition function, and partition function is definitely going to depend on T and of course also on V, therefore, there is going to be temperature variation in the properties, and that is what we are trying to establish. We are going to go ahead with a single chemical species, and we are going to look at how its thermodynamic property may be affected by temperature variation. That is the intention. Starting with Q translational, if you take a logarithm of the expression, you end up getting a form like this, and then if you take a time rather a temperature derivative, a partial derivative with respect to temperature keeping volume constant, then you see that it comes to 3 by 2 into 1 by T. And then if you recall, epsilon translational had a form like this, and then if you just substitute the outcome that the derivative came out to be 3 by 2 T, that is where you substitute, and you see that the E translational, that the specific internal energy in the translational mode will give you 3 by 2 R T. From the rotational equation, again by taking logarithm and then taking a derivative with respect to temperature, you get a form 1 by T. Plug it into the form for E rotational, the internal energy for rotational, and then basically what you are doing is you are just replacing this derivative with the corresponding form based on the particular mode of energy. Then you get R T. From the vibrational equation for Q, taking a logarithm and then taking a derivative, you get a form like this. Therefore, the vibrational internal energy will be a form like this, and of course, there is no closed form expression for the electronic energy. We already talked about it. From what we found here, for atoms we can therefore write the specific internal energy, of course, measured above 0 point energy, keep that in mind, is going to be equal to 3 by 2 RT plus the electronic energy, which is not specified here, but needs to be obtained from spectroscopic information or measurement. For molecules, remember, we have additional energy modes which can be excited compared to atoms. For atoms, it is only these two. So, we plug in the rotational and vibrational energy terms as well, and we know that specific heat at constant volume is defined by an expression like this. Therefore, for atoms, the CV will come out to be 3 by 2 R plus the derivative of the electronic energy with respect to temperature. We just leave it there without trying to get a closed form. For molecules, you get 3 by 2 R, the electronic part, as well as contributions coming from rotational and vibrational. And you see the dependence of temperature here. That means the moment you have vibrational energy excited, the CV will become dependent on temperature, and this is when you can say that. So, from a calorically perfect gas, we go to a thermally perfect gas. That is because of the temperature dependence here that becomes visible. So, statistical thermodynamics shows you specifically how the temperature dependence comes in. We try to conclude by saying that in this lecture we continued our discussion on application of partition function in obtaining the thermodynamic properties of a single chemical species, and how the thermodynamic properties of the single chemical species gas can vary over a wide range of temperature due to excitation of various energy modes was discussed. We showed the temperature dependence of CV, for example, for molecules through that discussion. Thank you.